So obviously, in order for us, we have the structure between our latent variable, the hidden variables, the state variables, and then the relationship between the measurement variables. And because we have discrete things running around, we don't have a dynamic, a dynamical system like we would in Kalman filters or particle filters. So instead, what we can have is we can specify how things are dependent on each other through conditional probabilities. Right, so these are called the state transition probabilities. And these are called the state emission probabilities. So basically, in order for us to tell people, to characterize a particular hidden Markov model, we have to tell them three things. So one is the state transition probability. So it is usually a matrix. So one assumption we usually make is that the state transition probability from x2 given x1 and x3 given x2, these are all the same. These are all the same probability distribution in that they don't depend on what the time index is, right? So you can see that simplifies the problem, because then I know that every time I see this arrow, it's the same probability distribution. And similarly, the emission probability, the simplest thing I can imagine is that if every single emission probability is the same distribution. So it would not, the emission probability at time 1 would not be this any different than the emission probability at time 3. So that's one assumption we can make to simplify the problem. So the state transition probability is a matrix. So what determines the dimensionality of this matrix?
How many dimensions your state has?
Right. So again, when I write this, what I'm actually saying is the probability that x2 equals some value given the probability of x1 equals some other value, right? So that means that this random variable at time xi is a random variable. So that means it could take on multiple values. It could take on square, rectangle, circle, and so forth. Diamond. So this is the dimensionality of my state, right? So this because this is random, this thing can be any four of these values. So that means what I have to specify is what's the probability that x2 is a square given x1 is a triangle? What's the probability that x2 is a square given x1 is a square? Probability of x2 is a square given x1 is a circle, right? So all of these probabilities I have to specify. So that's why it's a matrix, and the matrix, the dimensionality of the matrix depends on how many possible value my state can take. So again, by the notation changes, but by convention, we'll say that the dimensionality of the state is capital N. So this thing is an n by n matrix. And then the second thing we need to specify is the emission probability, which is also a matrix. So the notation, so this state transition matrix, at least in this class, we'll use the letter A to denote the matrix. And then, of course, every element of this matrix is element Aij. So this is the probability that xn is at state qi, given that xn minus 1 is at state qj. Okay. So again, the notation can be different. This is just how the book I was using choose to do the notation. So the emission probability, we denote this with a matrix B. So it's Bij, right? So it's also a matrix. And Bij here is the probability that Yn is, we'll use Bik. So Yn is some state Vk, given that Xn is equal to some state Qi. Right. So the emission matrix is actually the number of rows is n, the number of possible state values we could have, whereas the number of columns is am, because the observation variable being discrete can also take on am different values, right? So that's why if the emission probability matrix may not be a square matrix. Okay, and then the third thing we need to know is we need to start, you can think of this as a chain. So what we need to do is we actually need to start the chain at some state, right? We need to know, if we know what x1 is, say x1 is square, then we have some probability of observing y1. And then once we know that x1 is a square, then we have some probability of what x2 may be, right? And then we can have some probability of what y2 could be, then we have some probability of what x3 is, and then some probability of y3, right? So you see it's kind of the chain, but in order to start off this chain, I kind of need to know what is the probability distribution of the first state, right? So it's not, because this is a probabilistic model, I can't just go and, I don't usually go and tell you, okay, x1 for sure starts at the square state. I usually give you a probability distribution of at time 1, you know, x1 could be have a 25% chance of starting in the square, 50% chance of starting in the triangle, and then 10% chance of starting in the circle, and 15% chance of being in the diamond, right? So I don't usually go tell you that this is exactly the state it starts in, but rather I give you the probability distribution of what I think the first state value should be. So this is called the initial state probability vector. So the probability that the first state starts at state Q1, probability starts at Q2, and then the probability X1 starts at Qn. And of course, this being a probability distribution, the summation of all of these terms has to equal to 1. Okay, so once you have this, then you are fully specifying the hidden Markov models, right? So once you have this, you can write you can imagine that you can write a computer simulation that will actually, based on the distribution, simulate a state value, then generate a observation value, then generate the next state value, generate the observation, generate the next state, generate the observation, right? So once I tell you this, you can write a simple program to generate all the possible states and all the possible observations that you might see, right? So obviously it's important then to figure out where all of these values come from. And all of these values comes from having to learn what the state transition matrix, the emission matrix, and the initial state probability matrix from data. And you can see that since a lot of the stuff we're learning are matrices, if n is very large, right, or m is very large, this becomes the learning problem can become very complicated, because even if we have symmetry, there's a lot of terms that we have to learn. Right. So learning of the hidden Markov model, it's non-trivial. But even before we get to learning, even inference it's non-trivial. And the reason is because of the structure, the value in time could be very long, and also the state, the possible number of states you could be in, capital N and capital M, could be very large. So to answer any sort of inference question may be non-trivial. Okay, so last time we were talking about, just to give context to problem, one specific application which having to do with deciding, so given some observation set, right? So y1, y2 all the way up to yl, and we denote this with el or el. Okay, so given the observation, which are like say the special characteristics of acoustic signals or something. Given this, we have to decide which of the k-words was spoken. Right. So that means, so for each word, we have a hidden Markov model. Okay, and we're going to assume that someone did that's fully specified. So we actually know what the transition probability, the emission probability is from the learning phase. So now we're actually trying to answer a question, which is after we've learned the characteristics, we want to decide, given the observation, which of the k-word was spoken, right? And we decided that, of course, you could answer this question with the map estimator. In that, so I have, since I have k words, I actually have I also have k hidden Markov models. So M1, M2, MK, right? So of course, each Markov model comes with its own state transition matrix, state emission matrix, initial probability distribution, right? So knowing that each Markov model is this is not just one single number. This is actually wrapped within this Markov model. It has a large number of parameters. But the idea is that in order for me to decide which word it is given the observation, I can simply just, at a high level, what I want is I just want to find the model that has the largest posterior distribution given my observation, right? My y1 up to yl. But what this means is that this posterior distribution, we actually have to specify the prior distribution, sorry, not this way. The prior distribution of what the model is. So for example, maybe word 2 is more likely to be seen than word 1 or word 3. But supposedly I'm supposed to, in order for me to characterize the posterior distribution, I have to know the prior and then the likelihood. But in most cases, this is a uniform distribution, the prior, because I don't know which word is any more likely than any other word. So in that case, the map estimator, it's the same as the maximum likelihood estimator. Right. So the solution is the same. So what it is that it turns out that it's actually easier for me to work to maximize the likelihood function than it is for me to maximize the posterior, because the likelihood function doesn't require that it sum up to one over all possible models, right? So this is a distribution of M. This likelihood function, you could think of it as really a function of M, right? So once I tell you that Mi is, say, square, then I have a probability distribution. But if I change Mi now to a circle, then that's a separate probability distribution. So this is by nature, you could think of this as a function of Mi rather than it's not a distribution of Mi, right? Okay, so that's where we stopped last time. Okay, so ultimately what we learned is what we need to do in order to solve this problem, given these acoustic characteristics, decide which word was spoken, is to find the maximum likelihood, right? So in order for me to be able to compute the maximum likelihood, I have to be able to compute the likelihood. Okay, so remember that this notation, EL given MI, is really the probability of observation Y1, Y2, all the way up to time L, and then for a particular model, for the IF model, right? So for every model, you have this probability distribution. So the question is, if I want to do this directly, why is this difficult? Like, why is it that we're making a big deal about having to compute this particular probability distribution? Okay, so recall that this is the entire hidden Markov model, right? The entire hidden Markov model has this structure where you have both the latent state and the observations. So if I were to compute this probability of the observation given Mi, what do I have to do to the data? So the complete data of a hidden Markov model is really x1, x2, xl, and y1, y2, yl, right? The complete data that specifies a hidden Markov model really is the latent variable and the observation. But it's just that in practice, I don't observe the latent variable. They're hidden from me. I only observe the observed variable. But that just means that when I deal with this likelihood, I have to work with the incomplete data. So how would I, what do I have to do to the complete data in order to get the incomplete data likelihood? Right. So again, the complete data is all the states given the observation for a particular model, right? So what do I have to do to the complete data set in order to actually get this thing, which is what I need in order to decide which word was spoken?
We need MI.
Well, MI is given, so you already actually have MI. right? So it's already, MI is already given. So I give you, so MI, if you can think of it as all the state transition matrix, the emission matrix, and then the initial probability matrix. So this is all given to you. But what I'm saying is, from probabilistically, this is the complete data. This is complete data's likelihood, which, because I know these distributions, these state transition stuff, I actually know this. So how do I, but in order for me to determine which word was actually spoken, what I need is this likelihood, the observation likelihood. So the incomplete data likelihood. So what do I have to do in order to go from here to here?
Marginalize out the state stuff.
Right, exactly. So what you have to do is, really, your model considers both the state and the observation, right? So here I'm just telling you, okay, what the probability of seeing, let's say the state can be, the observation can be 1, 2, 3, right? I see 1, 1, 2, 3, 1, 3, 3 given for this particular model. But know that if just because I tell you that I observed 1, 1, 2, 3, 1, 3, 3, the state that could have generated this could have been square, square, triangle, 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 or square, circle, circle, triangle, square, circle, circle, right? So there could be, unless I'm very lucky and every state only generates a particular observation, there could be multiple states that lead to the same observation, right? So in order for me to actually characterize this probability, I have to sum over all the possible states which could have generated this particular sequence of observations, right? So it's because of that summing over part that can become very time consuming, because again, each one of these states could have a dimension that can take on n different states, and I have L of these possible states, right? So if time is very long and the hidden state can take on many different possible states, then this marginalization becomes very time consuming, right? So again, if you have the trivial problem of the particular state can only take on 4 values, like square, rectangle, square, triangle, circle, diamond, and L is like, I don't know, 50, okay, L is like, I don't know, 10, then you don't have a problem. But if L is like 500 and N can take on like 20 different values, then you start having problems, because the number of possible sequence you will have to sum over is N to the L. And anytime you have numbers to some power, this thing can increase dramatically very, very fast. So that's one thing, is that I know exactly what I need to do, which is to compute this likelihood function for all my possible models, right? I tell you that my observation, the observed value, is 1, 1, 2, 3, 1, 3, 3. And if you know the likelihood, you can tell me, okay, the likelihood of 1, 1, 2, 3, 1, 3, 3 for model 1 is 0.2. The likelihood function, the likelihood value for model 2 is 0.7. And the likelihood of observing the sequence for model 3 is 0.5, right? So if you have a magical thing and it tells you this, and suppose we're only working with 3 words, which word would have generated this particular sequence of observation?
We're at M2.
Right, exactly, right. So that's how the maximum likelihood function works. I give you these observations. Right, so you're now looking for a probability distribution of these observations. You only need to tell me it's not a distribution of these observations, it's just the probability of given this particular model of seeing this observation. And obviously, if I have M2, I have the highest probability of seeing this particular observation. So by the maximum likelihood, I should say that the most likely model is M2, right? The most likely word is M2, right? Okay. Does that make sense that this thing, even though it looks like a probability distribution, this thing itself is actually a number? Maybe I think that's the part that it's a little bit different. So it's usually when I write something like this, right, you assume that, oh, this must be a distribution. This is a probability distribution. So when I write that, I get, okay, the probability of x1, like I have to specify this entire probability. Right. That's usually when you see this, you see, oh, it's a probability distribution. So you're starting thinking about vectors and stuff. But does it make sense that when it's the likelihood, when it's like this, that this is actually a scalar value and not a probability distribution? So you can forget the m. So if I have probability of y1, y2, y3, and probability of x1, x2, x3, this I tell you it's a number. And this I tell you it's a distribution. Does that, in the context of hidden Markov models, do you see the reason why this is a number and this is a distribution?
Yeah, that makes sense.
Okay, why?
Because when you go from your like state to your observation, there's like a corresponding probability of making that like leap, I guess. I don't know. And then like each of the x's have their own like distribution before doing
Okay,
like observation.
but each of the observation is also a random variable, right? The observation itself also has a distribution, right? So like I said, I could have what's the probability I see, right? Like the x's, it's a random, this thing is a random variable, but the y observations are also a random, oops, that's it, right? The observations are also a random variable, right? It could take on capital M different values.
Oh, I see.
Right, and this one can take on capital N. So here, I think it might be a notational thing. So that's why it's important to get this clear, because it's kind of more of a notational thing than a conceptual thing, right? So I guess what I'm saying is what you're saying, the reasoning is not quite correct, in that both the observation is also a random variable, right? When we think of Kalman filters, the observation is the state plus some random noise. So every time you do this at y2, even if the state stays the same, the observation might be different, right? Because we also have, it's not guaranteed that if you get a triangle as the state, that you will always observe a particular output, a particular observation. There is some like non-zero probability of getting, instead of the same observation as the previous time, of getting different observation. Right. So in that case, the question is, I mean, so here's where the like the understanding is actually sometimes difficult because of the notation, and I'm not quite sure what's the way of notation is. It's actually what's keeping it. Why is it that this, if I write this in the context of the way I describe the Markov model, this thing I expect to be a distribution, but this thing is a number. And note, I got rid of the given mi because that doesn't matter, right? The given mi just means that for different mi, I get a slightly different distribution and I get a slightly different number. So what is x and what is y?
Are you just asking like x's state, y's observation?
Right. So that must be, so the reason, I guess what I'm saying is, the hint is, this is a distribution and this is a number. Obviously the p part, the probability part, has to be the same, right? So the only way that these two things could possibly be different has to do with inherently what x and y is, right? So x here is my state, y here is my observation, right? So you should at least know that, again, if I use a different set of variables to define my hidden Markov model, this will make no sense, right? But the reason it, quote unquote, it makes sense is because I always use x to define my state, and I always use y to define my measurement. So now, so the state is, latent or whatever, so unobserved. And obviously the observations are observed. So when I say unobserved and observed, I guess the other way of saying it is given and not given, right? Because if I observe something, then I know exactly what value it is because I observe it. You assume the computer knows. If I don't observe something, then I don't know the value. So then the question is, if this is not given and this is given, why is it that this is a distribution, but if I write this is a number?
Because given is exactly number, but the unobserved is not given, it's a probability, right?
Okay, I need to be a little, so this is also a probability, right? So
but why you have known?
Okay, good, right? So I know because the y's are given, so I actually know what this is, right? So notationally, I write this y1, y2, y3, but that's because I'm trying to cover my bases and not work with a specific problem. But in your mind, you could think of it, okay, I know y1, y2 is given, so let's just say that is 1, 3, 2, right? Again, I don't want to be so dedicated to a specific state that I can't use this problem for anything else, but I know y1, y2, y3, so I'm going to assume that it's 1, 3, 2, right? So now, instead of writing this variable placeholder y1, y2, y3, I can write the probability of 1, 3, 2, right? So now does it make more sense why this is a distribution and this is a number? Yes, no?
Yes.
Okay, so why?
Because I think, why just like some words you have observed, So you just to use MI to calculate the probability of xi. So xi might be a square triangle or circle. Yeah, and each one have a probability.
Okay, so I guess, okay. So I guess the thing is this, because I observe y1, y2, y3, when I write this, you can always think of this as actually writing the probability that y1 equals 1, probability that y2, probability of y1 equals 1, y2 equals 3, and y3 equals 2, right? That's what this notation really means, because I observe the actual y value. So this is why this is a number, because it's really just telling me what is the probability of seeing this particular given observation, right? But when I write this is really a probability distribution, because you need to specify what's the probability that y1 takes in a particular value, say triangle, square, circle, right? Or circle, triangle, square, right? So there's actually, there's 4 to the 3 possibilities here, right? So that's why this is a distribution. So the thing is with notation, I cannot keep writing this, because this assumes that y1, the yi's have to be a numeric output. But it's like this problem, this might not be a numeric output. This could be a vector or, something. So it doesn't, I don't want to be married to the fact that y can only be 1, 2, or 3. But you can see that 1 is really the probability of the observation, the given observations in a particular state, whereas the other one is a probability distribution, right? So that's it. That doesn't mean that y1 itself is still a random number. So there is also a distribution for y1 here, which is the probability that y1 equals to 1, the probability that y1 equals to 2, all the way down to the probability of y1 equals to n. Right. So you have to be a little bit careful when you look at how the observation probability is written. Is when is this thing a actual variable versus when is it a assigned value, right? I could just ask you, what's the probability, because I'm given y1, what's the probability that y1 equals to 2, right? That's a number. Whereas if y1 is a random variable, then it has to be specified as a distribution, right? Okay, so, but that's how the maximum likelihood works, is that I actually know, if I know the distribution, so given my model, what I need to do is I need to compute this probability efficiently, and then I can just tell you which word it is. But what's keeping this from being able to compute efficiently is the fact that I don't know which one of the sequence of states generated the given observation, right? So I have to sum out the possible number of states in order to get this probability, the actual number, the probability of seeing this particular sequence, right? Okay, so what I need is not, what I want to avoid is having to sum out the distribution like this, right? Because even if here, like for example, I know what the observation is, even if I know the observation, so that means I don't sum over the observation, I still have to sum over the state. And again, this thing takes capital N to the I operations. So I don't want to have to directly compute my likelihood this way. It could be very time consuming and inefficient. So what I'm hoping for is like the Kalman filter once again, and the particle filters, is that what I want is a recursive way of doing this. So I also am looking for a recursive algorithm where, because again, I have data in time. What I want to do is be able to take the solution from the previous time, do something to it, and now I have the solution to my current time, and then do something to this, then I'll be able to update to my solution to the next time. Right. So that's what a recursive thing is. It's I don't have to compute everything from scratch like this. I want to be able to keep updating it. So in the hidden Markov model, this recursive algorithm is called the forward backward algorithm. So there's actually, so forward means forward in time, backward means backward in time. So there's actually two ways of doing this. You can go forward in time or you can go backward in time. So the reason why you may want, you need one way to go, one to go forward and one way to go backward is if you didn't have your time, if you didn't have your signal, if it's an operation, an application where you still have incoming data, right? The data is still, you're still getting incoming observations, then the only way for you to do is to go forward in time, right? Because you're still not seeing all the data. You have to keep going forward in time. But it could be that you're working in an application where you have finite observations and the observation stops at some finite time. Like you know you will never see future observations. So in that case, it's actually more efficient to go both forward and backward simultaneously, because this can use computer, you can go forward with computer 1, you can go backward with computer 2, and they can do this in parallel, and they'll meet up somewhere in the middle. So that's one reason why you might want you might want to go backward, is to make things a little bit more efficiently. But obviously, in situations where you still get incoming observations, it's kind of tricky to go backward in time when you don't even know what the end is. Okay, so we'll talk about the forward part first. So like its name, algorithm. It starts at time 1, so starts at n equals to 1 and goes forward in time. And the thing about, so the forward algorithm, it does not require the availability of all the observations before you can proceed. So you can still keep going. The observations can keep growing. Okay, so we're going to define, so recall that before what we had to deal with was the entire length of observation, right? All the way up to time L. And so that way we called EL. But now what we want is we want a recursive algorithm that doesn't just go the entire length. Instead, we want to go, some middle way. So we'll say the middle part is n, right? So we're going to define instead the set of observations up to some time n as en. And so obviously these observations, I know what they are because they're the observed values, right? So this is really y1 equals to some observation, y2 equals to some observation, yn equals to some observation. Right. But again, this is painful to write, so I write this. So En is my set of observations up to time n. Right. So what I want is, again, like I can't just define the probability of the observations. I also need to consider the state. So instead, what I want to do is I want to consider the observations up to time n, the state at time n being in a particular value, and for, of course, this is all for a specific model, right? So this I'm going to define, instead of writing this all the time, I'll define a new variable, which is called the forward variable. So that's the, so the forward variable, the way it's defined here is actually, it's a number, right? So you see that this is a number because I know exactly what the value of y1, y2, and yn is, and this thing tells me the state xn is at the state qi, right? So all of this is specified. So therefore, this thing is really just a probability for a particular model of seeing the sequence of observations and the state at time n, right? So
we know MI now?
you always know MI. MI is given.
Okay.
Right? So what you do is you create this for every model, right? So you have this for M1, M2, M3, right? So every time you have something that's given, that is known. So the way this works is you create these things for every single model, and then you basically at the end you compare the likelihood, right? So right now what we're doing is we're going to find a way of computing this in a recursive, efficient manner.
Okay.
Right. So you always know M1. You assume you know the hidden Markov model. So again, what it's going to become is going to become tedious to keep track of all the, the KMs, right? So in your mind, know that this one is separate for every single model, but it's just easier to talk about one particular model, right? Okay. So that's what the forward variable is. Know that it's a scalar. It's not. It's a probability, but it's. I mean, it's a scalar probability. It's not a probability distribution, right? And again, this takes forever to write. So what we want to do is we want to write it like this. Right. So I'm going to drop the I because it's, again, tedious to write the different MIs. But you know that this thing exists for different MIs. Okay. So obviously, this forward variable exists for every time, right? I could have time 1, time 2 for a different state. I could have it for the same state. I could have it for the different state. Times 3, right, all the way. Time n. Time n plus 1 in a different state, right? So you see that I can define this. So notation-wise, this P1 at time I is the probability I observe this value for a time 1, given that at time 1, the state is in state QI for my particular model, right? Similarly, the probability I observed the observation Y1, Y2, given that X at time 2 is in the state QI, given M. The probability I observe Y1, Y2, given that the state at time 2 is QJ, given M, right? So note that this is why these things are scalars, because this gives me a different probability than this, right? So obviously, so the general form is alpha n I. The probability of en xn is qi given m, and then alpha n plus 1j, probability of en x at time n plus 1 is qj given m. Right. So if j equals to I, then the state if what I'm assuming is that the state at time n, if I equals to j or j equals to I, then the state of the Markov chain did not change from time n to time n plus 1. So what we want, again, because this is a recursive thing, what we really want is we want to have a way of expressing this forward variable at time n plus 1 as some function of the forward variable at time n, right? So that's how that's what the idea behind a recursive algorithm is, that if I know this, then I just need to do something to this, whether I add something or multiply something or divide by something. I want to do something to this in such a way that I'm guaranteed that I get the next forward variable. Right? So what that something is, well, it's not too complicated. It does get notationally hairy to do. So what you want to consider, so here you don't have to follow along exactly, but note that obviously you can see that it's not too crazy. Oops. Let me see here. Yeah, plus 1. It's not too crazy to be able to do something to alpha n in order to get alpha n plus 1, right? Because alpha n plus 1, at least in terms of the observation variable, you see y1, y2 all the way up to yn already, right? So it becomes just, you just have to modify it slightly to consider what happens if I'm in this particular state at time n. How do I get to that particular state at time n plus 1, right? So you see that there's not too big of a leap in order to do that. So let's see. I'm not going to. Oops. So I'm not going to derive it. The notes have the derivations. So, but you can see that the flavor is. Let's see. Right here, what you have is y1, y2, yn. Here, what you have is y1, y2, yn plus 1, right? So one thing is the observations are the alphas already have the observations from y1 up to time yn. But again, like I said, you'll probably have a flavor of transition of if I start at qi at time n, how do I get to qj at time n plus 1? And if I'm at qj at time n plus, if I'm at qj at n plus 1, how do I get this observation at yn plus 1, right? So without proof, what you can see is that what it turns out is that this function, this recursive function, actually ends up being the forward variable at time n times the state transition probability times the state emission probability, and then sum over I equals to 1, 2. Okay, right. So because at time xn, right? So here represents at time the forward variable alpha n. Part of it represents at time xn, the probability, the state is going to be at qi, right? But because this is the latent variable, I don't observe which state the system is actually in at time n. So I have to I have to marginalize. I have to take into account all the possible state the Markov model could be in at time xn. That's why you have the summation from 1 to capital N. That's just to take into account that at time n, I could be in any one of these 1 to the capital N possible states, right? So here, this is the state transition probability. So the probability that my state is going to be state Qj given it was in state Qi, right? And this is the emission probability. So the probability that if I'm at state Qj at time n minus 1, what's the probability of observing this additional observation, right? So this is a number, right? Okay, so that's the recursive forward update. So again, it's not, you can go through the derivation, and it's not too difficult. The notation becomes very hairy, but you see that it has all the elements. You can look at the form and kind of have an intuition that it will have all the elements you need. And of course, I know the state transition probability and I know the state emission probability because I actually know the model, right? So these will be specifically, if I'm working with model M1, then I use the state transition probability and the emission probability of model M1. If I'm working with model M2, then I use their corresponding state and emission probabilities, right? So that's the update. So what you can see is now instead, so if I'm still interested in my likelihood, right? So I'm still interested in the probability, y1, y2. So here, what I have, the alpha n plus 1 j at j is, this is the probability of y1, y2, yn plus 1, x of n plus 1, qj for my particular model. So what I can do is I can consider this as y1, y2, y3, all the way up to, yl, x at time L is equal to qi given m, right? So what do I have to do with this? What do I have to do to this in order to get the actual likelihood, right? Because this, note that this is alpha Li, right? And I know that I can compute alpha Li from alpha L minus 1, which can be computed from alpha minus 2 and so forth, right? So if I have alpha Li, then what can I do in order to get the actual likelihood here? Because we showed that the forward variable, right? The forward variable is easy to solve recursively. We just keep applying this equation. We start with alpha 1. We multiply it by the state transition emission probability. We get alpha 2. We multiply it by this thing. We get alpha 3 and so forth, right? So we know that computing the alpha recursively is easy. But once I have the alpha, say alpha L, what do I do to this in order to get the actual likelihood, which is what I need in order to decide what this word is? Right. So you look at the distribution. This is the distribution I need. This is the distribution I have. So what do I need to do to this distribution that I have in order to get to the distribution that I need?
So yi and xl is independent?
Sorry, what?
Yi and xl.
No, it cannot be, right? Because you see the structure, these cannot be independent because XL determines YL, but XL is dependent on XL minus 1. So there's no independence. You cannot, I mean, if it's independent, then these things, this graph will be disconnected.
Yes.
Okay, so it's not independent. But what can I do to this probability distribution in order to get to this probability distribution? Right, so this is probability of y1, y2, yl given m. This is y1, y2 all the way up to yl, xl given m. So what can I do here to get to here?
Take the sum over like QIs.
Exactly, right? So I need to marginalize. So here, this is just a probability distribution with one additional variables, right? So what I need to do is I need to marginalize out what is all the possible at time, the state at time L, it could be any one of these Q1 up to Qn states, right? So I need to consider x at time L is Q1, Q2, or Qn, right? So that's the only thing I need to do is that once I marginalize out XL, then I have my likelihood, right? So basically this thing, again, because of notation, it can be, this is the forward variable. So, right. And so at the end, you get, this is your likelihood. But the reason that this is much better than directly computing the likelihood function, which means that you have to sum over all the possible state from time 1 to time L, the reason this is better than doing that, here you only have to sum over the state at time L. You don't have to sum over the state at time 1, time 2, and time L. The reason you don't have to do this is because the forward variable has a recursive form. So every time I find the forward variable, I'm actually already marginalizing over the state at that time. So I don't have to wait until the end to do the summation over the entire sequence of state. I can just keep going forward little by little, right? So that's what makes this a more efficient than if you were to directly compute this, which again, mathematically is correct, but computationally it's time intensive. Right. So this is one way. So one way is the direct method of marginalization. The other way is to come up with this recursive update. And computationally, this one is faster than this one. This one might actually be impossible if capital N and L are too large. Okay, so once you have this, then obviously, right, you have the likelihood, and I know you can find the maximum, and you know exactly which word it is. Okay, so Wednesday we'll talk about we'll just briefly talk about the backward algorithms, and then we'll talk about learning the parameters. Okay, yeah, so, okay. Any questions?
No.
Okay, I'll see you guys on Wednesday.